Okay, yeah, thanks a lot for that introduction, and thanks for the organizers for putting on this conference. So today I'm going to be telling you about our upcoming work on studying the self-correction properties of layer codes, and this was joint work with these collaborators, Libor, Sunny, Shinho, Alex, and Eugene. So yeah, I guess I'm a QEC person, so usually I think about error correction in the active setting, where we have some code, and then we're continually extracting the syndromes using some circuit. We measure these stabilizers, then we apply some classical decoding algorithm, and then we can apply corrections after every step. So we just keep repeating this process. But there's another interesting setting, which is that of passive QEC, where we could just try to make the environment do all the work for us. And this is kind of what happens for like classical hard drives, right? If you unplug your computer and you turn it off, the information is still going to be there. So can we have some kind of similar thing for quantum memories? And the advantage, if we can construct such a system, would be that potentially it would be more scalable, because you engineer this interaction, then you just have many qubits, or I guess many physical qubits together, and then that would just naturally allow you to keep the memory from corrupting. And additionally, while we're just storing the information, then we don't need to actively do anything, and it will just kind of be there. And so today, I'm going to tell you about our investigation into these layer codes, which is a very nice construction by Williamson and Baspin. It's a three-dimensional topological code that has a lot of very good properties, and potentially leading to some self-correction. And so the plan for the talk is that I'll first give some background on quantum memories and what is the definition, what has been tried so far, and also provide the overview of this layer code construction. And then I'll get into more of our work, which is considering layer codes in a slightly different scenario where we actually use a random input code. So we show that actually when you put in a random input code, it also has a lot of interesting properties. We show that we can decode these layer codes. And finally, I'll give our result about that these layer codes are actually supporting partial self-correction. And then I'll also show some numerics that we did to kind of support our results. Okay, good. So self-correcting quantum memory. So what we want to do is store the quantum information that we're trying to protect in the ground space of some many-body Hamiltonian. And ideally, this would be robust to noise. So we want it to be robust to, let's say, like finite temperature effects, and also some local perturbations. And so the criteria that we want for self-correction is that this Hamiltonian should be locally embeddable with some bounded terms. And ideally, I guess it should be in some low-dimensional Euclidean space in order for it to be practical. And we want to have the property that below some critical temperature, we can actually increase the memory lifetime as we scale up the system. So for full self-correction, we would want this memory lifetime to diverge as we just increase the system bigger and bigger. But sometimes that's not possible, so we can also have this partial self-correction, which is that the memory lifetime is kind of increasing, maybe up to some critical system size, which could, this critical system size could be temperature dependent as well. So this is kind of specifying what it means to have self-correction, but like, what does it mean for the information to be still stored in the system? So we want to have some way of recovering the information. And in general, this way of recovering the information may not be efficient. So in that setting, we would still call it self-correction, but the decoding would not necessarily be good. But if the system is also efficiently decodable, then I will call those kinds of systems like a quantum memory. Okay, so then how do we find these systems that could support self-correction or are quantum memories? So one very nice class of Hamiltonians is ones that are defined by stabilizer codes, because we know a lot about stabilizer codes from error correction, so we can kind of use a lot of those tools. And so we can define the commuting polyhamiltonian, which is minus the sum of all of these stabilizer generators. And in this setting, actually, there are some no-go results that say that for certain types of systems that self-correction is basically not possible. So actually, all 2D stabilizer codes are not good. For example, the toric code, will just have these anionic excitations that are allowed to propagate without increasing the energy. So basically, that's not going to be able to store any information. You can just implement a logical operator very easily at any non-zero temperature. In 3 dimensions, the no-go theorems are much more restrictive. So there's one by Benny Yoshida that says that if the 3D system is translationally invariant and also supporting a constant number of logical qubits, then that will actually not be able to have self-correction. But that's pretty restrictive, so it may be possible to get around this no-go theorem. Of course, we could also consider other Hamiltonian systems, maybe ones defined by subsystem codes or quantum double models, string net models, but those are going to be quite complicated to analyze. So that's not really the setting that I'm considering. So there's one concept that seems quite important for self-correction, which is that of the energy barrier. And the energy barrier is basically the cost that the environment has to pay in order to implement some logical operation on your system. So it's the cost of changing this encoded information. And the way that we define it is that we can say that we have a polypath, which is just a sequence of poly operators that differ at one location between consecutive polys. And then we can say that the energy of this polypath is going to be the maximum energy or the maximum syndrome weight of any poly in that path. And so then the polypath of a given poly operator is going to be the minimum of this energy over all possible different polypaths that end on this operator. And for a given code, then we can also do the minimization over all possible logical operators. And this would capture the energy that it would take in order to implement this logical operator. So in general, we would want to have a very high energy barrier in order to have a self-correcting memory, but this is not like a sufficient condition necessarily. So, right. Okay, so what is actually known about what's possible and what's not possible? Well, I mentioned that in 2D stabilizer codes are basically not good. But in 4D, we do know that the 4D toric code is self-correcting. And if we go to, I guess, quantum LDPC codes, this is not really embeddable in Euclidean space. Maybe it's like infinite dimensional space. But also we know that these quantum LDPC codes also support self-correction. And so in 3 dimensions, it's kind of what's not really known so far, and kind of also the most interesting setting because we live in 3 dimensions. And so in 3 dimensions, there's been a few attempts. So there's this qubit code that has an energy barrier scaling logarithmically with the system size. And this supports partial self-correction. And also, there's also this welded toric code that actually has better energy barrier scaling, and is also supporting partial self-correction. Okay, so, but we don't know if full self-correction is possible. Yeah. Yeah, I think. Yeah, I guess so, because, yeah, if you can't have an energy. Sorry? Like, is it possible to get partial self-correction in 2 dimensions? Yeah, because I guess if there's no energy barrier, then probably it will not be possible. Okay, so now let me start to explain a bit about the construction that we're considering, which is the layer codes. And so this is a mapping that you can think of it as it takes in any CSS code, like no restriction on locality or anything. After it takes in this code, it outputs a geometrically local CSS code. So a topological code in 3 dimensions. And also the check weight will be at most 6. So how this works is, for every qubit of the input code, we're going to put a surface code patch. So in this case, if we have 4 qubits, then we will have 4 surface code patches. And the way that I've drawn these figures is that the dashed lines are the rough boundaries and the smooth lines are the smooth boundaries. Okay, so we have a bunch of surface code layers. And then also, for every X check of the code, we're going to place another surface code layer in the horizontal direction. Okay, and these surface code layers are going to have smooth boundaries, so all the boundaries are going to be smooth. And then for every Z check, we will place another surface code layer, but this time in the third direction, and it will have all rough boundaries. So far, we just have a bunch of surface code layers that are decoupled in 3 dimensions, so that's not really doing anything. But then the idea is that they're going to be coupled in a very particular way, which is dependent on this input code. So if a given qubit is in a certain X check of the code, then the 2 corresponding surface code layers, when they intersect, they're going to have a non-trivial defect line. Okay, so there's going to be some special rules for how you couple these layers together. But if the qubit is not in the X check, then they will just pass through each other. And also, where the X checks and the Z checks intersect, there's also going to be some defect line segments. And so the interpretation that I like for these layer codes is that we're essentially concatenating the original CSS input code with the surface code. So you can think of that as the qubit layers. But now we need to implement the parity checks, the outer parity checks from the input code. And normally that would be very non-local, very high weight. And so we add these extra layers in order to kind of implement those checks to decrease the weight via lattice surgery. Okay, so this construction is almost the same as concatenating, but with some extra steps to make it geometrically local. And the way that we normally analyze these code is not directly through the stabilizers, although that could be done. But the easier way to think about it is to consider the quasi-particle excitations that happen. Because we have a bunch of surface code, so we can think of violations of the X or Z stabilizers as these E or M anyons. And away from any of the defect lines, they're going to have the usual fusion rule. So like the E excitations can just move around, and 2 E excitations will annihilate each other. But at these defect lines, they actually split. So here I've drawn some kind of the rules, which that if let's say you have an E excitation that goes through, on the Z layer, goes through a line defect with the Q layer, then it will actually split into 2 different excitations. Okay, so it will branch out. But I guess if it's traveling along the Q layer, then it doesn't really split at the defect line. And so, there's 3 different types of line defects, and I've drawn the rules for all 3 of them. But the idea for this is that, these errors are going to be energetically suppressed, when they're trying to pass through one of these defect lines. So we would hope that, with all of these defect lines, then we can actually kind of suppress these errors. Okay, and now that we have the construction, so what was shown by Williamson and Baston was that if we input some CSS code, that has parameters n, k, and d, and let's say the max check weight is w, then the layer code will inherit a lot of the properties of the input code. So in particular, so the number of physical qubits is going to be roughly n cubed. And then the number of encoded logical qubits is exactly k, because it's basically concatenation. And then the distance will be n times d over w. And then the energy barrier is going to be the energy barrier of the input code, but divided by this w squared factor. So for example, we could input some of these asymptotically good quantum LDPC codes, like the quantum Tanner codes, which have k and d scaling linearly with n, and also the energy barrier. And then you would get the layer code that saturates the BPT bound. So it's kind of optimal in 3 dimensions, so that's pretty nice. And also the energy would be scaling as n. So the relative energy barrier is still decreasing because we have more logical qubits, but that's what is proven. And so if we want to use these layer codes as self-correcting memory, then we kind of have this puzzle, which is, we have this energy barrier, but at the same time, if you have an LDPC code as input, that means, by the construction, then we're not going to have a lot of defect lines, right? Because there's only defect lines if a given qubit actually is in the support of a check. And so we're going to have a situation where you just have a bunch of surface code layers with very sparse defect lines. Most of the code is just surface code. So actually, maybe you would expect it not to be self-correcting. Sorry?
So we're talking here.
Yeah.
The statement about sparse because it's true that blend sparse, right?
Yes.
We also have a green defect.
Yeah, so the green defect is when it's related to when an X check and a Z check have common support. So if it's LDP. Yeah, so those will also be sparse. Yes. Okay, so it seems like LDPC code. Oh, yeah, another question. Yes. That's what I'm getting to. Yes. That's good. Yeah, good. So so we are using HDPC input code, and so the idea is that. Actually, it turns out that we can show that it is partially self-correcting, but I guess we were trying to show maybe explore whether or not it's actually fully self-correcting. And actually, when we started this project, we didn't know that either. So, the motivation was kind of that we just wanted more defect lines so that the excitations can split more. Okay, good. So yeah, anyway, we want to consider these HDPC codes, as we like to call it. And to do that, we could just consider some random CSS code input. So that is that we just choose the parity check matrices HX and HZ uniformly at random. Every single entry is random, but we subject to the condition that that HX times HZ transpose is 0 in order to get the commutation. And so this will basically get a lot of defect lines, and we might expect that to be good. However, one problem with working with these HDPC input codes is that a lot of the original proofs will basically break down, and because all of these lower bounds that we have are kind of divided by W, or the energy barrier is scaled divided by W squared. So if W is almost going to be N, then that is not giving very useful bounds. And so what we did was we actually prove that if you input a random code, then with high probability, you can actually recover almost the same theorems up to logarithmic corrections. So not necessarily every single time you will, but most of the codes are going to be good. And so what we can show is that the layer code will have parameters n cubed, n, and then the distance will be n squared over log n with high probability. And also the energy barrier will be n, but divided by this log n with high probability. And so, let's see. So some of these proofs are quite involved, but let me just give a high-level overview for the distance. So remember, this construction is kind of like concatenation. So the logical operators of the code are also what we call these quasi-concatenated logical operators. So you would take some logical operator of the input code, have some vertical strings on it, as that would be the case for concatenated representatives. But then because of these fusion rules, you get extra excitations, and then you would just match them. So this is one possible representative of a given logical operator. And so, if these were the only representatives, then actually we would be good, because that would basically give the correct scaling of the distance. But the problem is that, sometimes we can have this bad scenario where we can somehow clean off the support from these Q layers onto a Z layer. So, oh yeah, by the way, this is for Z logical operators. Okay, and then that would actually significantly decrease the weight of this logical operator. So sometimes this can happen, but what we do is use a GV type argument where we're just counting the possible locations of all possible strings, or maybe like all possible, like not having too many strings. And we show that all of these arrangements, basically it's going to be unlikely to coincide with one of the actual logical operators of the code. So that basically shows that there's no low weight logical operator. Okay. Okay, now let me start talking about partial self-correction a bit. So there's this very nice lemma in this Bravi and Ha paper, which is basically saying that if you have a decoder that can correct errors with a low energy barrier, right? So if the error, cannot be created, the error cannot be created by a low energy path. Oh, sorry, it could be created by a low energy path. If this decoder can correct all of those types of errors, then you basically have then you basically have good memory lifetime up to a certain point. Okay, so also, we want to thank Dom for telling us about this theorem, which somehow we missed while reading the paper. Anyway, so the conclusion is that the memory lifetime is going to be scaling as e to the beta times the energy barrier that you can correct to at this critical system size, which is exponential in beta. And so this means that if you can have a decoder that corrects, this means that if the code actually just has an energy barrier, then you already get partial self-correction. And this is using a decoder that could possibly be inefficient, which we call the energy barrier decoder. And the way that this decoder works is that it just tries all possible paths and finds the one that doesn't cross the energy barrier. Okay, so it's kind of a naive decoder, but it will be some decoder that allows you to do this. Yeah.
Do you need to assume some particular model of time evolution for this theorem?
So I think, you need to assume like the typical assumptions, like, weakly coupled to Markovian and local. Right. So, I mean, of course, this is getting partial self-correction, but maybe we also want a memory, right? Maybe we want the decoder to be efficient. So let's discuss some decoders for this layer code construction. And actually, through the course of doing this project, we came up with 3 different decoders, or I guess at least, this one maybe is adapted. But we have this RG decoder for layer codes, which is good against stochastic errors, so we can prove a threshold for this kind of decoder. And this kind of decoder kind of works by clustering these syndromes together, which, because if the errors are local, then the syndromes are not going to be too far apart. So then that's why we expect that the clustering to be good for this. We also created this concatenated decoder, which is good against adversarial errors. And the way that the concatenated decoder works is kind of we correct low-level syndromes on the surface code first until at some point it gets stuck, and then we invoke some decoder for the input code, and then that will allow you to correct the rest of the errors. So this is good against adversarial errors. And we also have a simplified version of this concatenated decoder, which can correct against errors that have low energy barrier. And I guess this is actually the decoder that we want to use for self-correction. Okay, so I'll explain a bit about how this simplified concatenated decoder works. So let's say we have this portion of a layer code, and we have these 2 syndromes in the red dots. Okay, so in the first step of the decoder, we simply just match every single excitation on the Z layer to the top boundary of the code. So remember, the top boundary is a rough boundary, so it can condense these E anyons. Okay, so we do this, and this could possibly create more excitations on the X layers that it passes through, but that's okay. And then we do the same thing on the Q layers. We just match everything to the top boundary. And this could also create more excitations, although I guess in this picture it doesn't, because it doesn't cross any X layers. And then, so the thing is that at this point, we want to get rid of the excitations on the X layers now. But we have this problem where it could have an odd number of excitations. And because the X layers the boundaries don't condense any E anyons, then we're kind of stuck now. So this is the part where we have to invoke the input code decoder. And what we do here is that all of the X layers that have an odd number of excitations, we can treat that as a syndrome of the input code, right? Because that's a subset of the X checks. So we give that syndrome to an input code decoder, which will output back some correction, which is a subset of qubits. And then on those Q layers, we will apply a vertical line for all those qubits in the correction. And that will, you can show that after you do that, then it will always be an even number of excitations on every X layer. And then we just match them up to get rid of that, to get rid of that syndrome. Okay, so then what we can show is that for this particular decoder, that actually with high probability over the input code C, because remember the input code was random, then this simplified concatenated decoder can correct all errors with low energy barrier. So the energy barrier should be less than n over log n. So that was also the energy barrier of the code itself. So for any error that has energy barrier of this size or less, then it can actually correct it. So the intuition is kind of that if the energy barrier of E was low, then in some sense it's already close to a code state. So there's not, as long as we don't perturb it too much, it should actually be good. And that means that in steps 1 and 2, when we're just matching everything to the top boundary, we're only creating at most n over log n strings, because there can only be at most n over log n syndromes to start with. And so at that point, we can invoke a decoder of the input code that can kind of correct errors up to this weight. And then that will actually allow you to return to the code space of the layer code successfully. Okay, so then the theorem that we can prove is that if we use this simplified concatenated decoder, we can get memory lifetime up to e to the beta, because it can because it can correct errors of energy barrier L over log L. Okay, so this is kind of the summary of, so we also explored slightly different scenarios, and this is kind of the summary of all of the results. So actually, even with the simplified concatenated decoder, it's unfortunately not efficient, because at some point we invoked the input code decoder, and I kind of just said that, okay, we can correct all errors up to n over log n, but for random code, this is not necessarily an efficient process. Although it's, this decoder is still better than trying every single polypath. So I guess we have that. But if we restrict to energy that's less than log n, then we'll be able to have an efficient decoder, because you can just try all the possibilities. But then the price you pay is that you will only be able to have memory lifetime that's e to the beta squared. Also, if we input a good LDPC code, then because we know that the good LDPC codes have efficient decoders, then that will allow us to actually get memory lifetime up to e to the beta, and the decoder will also be efficient. Okay, great. So I guess that's all of the theory. So let me just show you one slide on the numerics that we did. So what we did was, we would just initialize the state in the code space, and then apply, couple it to a thermal bath at non-zero temperature with all of these assumptions. And I guess operationally, the way that we do it is we sample qubits I and apply the error with EI with probability that's related to, if it's increasing or decreasing the energy. And so we do this, we repeatedly do this process and repeatedly try to decode to see if we're still have the memory alive. And the memory time is going to be the first time that the code cannot be decoded. And so this is kind of the plot that we get. So we're plotting the average lifetime against the input code size for different ranges of temperatures. So, we're kind of seeing that as we decrease the temperature, then the memory lifetime is increasing up to a certain point. Right? So that's kind of consistent with partial self-correction. Okay, and now let me mention, this is also one advantage of using these random HTTC codes as input, because for a lot of these codes, actually, like especially when you get to like size 40 or something, you end up with like 100,000 qubits or something. So we need to have good interpolation between the different code sizes. So it's really important for us to be able to have input codes of arbitrary sizes. And also, if we were to use good LDPC codes as input, we don't really know what sizes we would have to go to have some members of that family. Okay, so I guess just to sum up, we proved partial self-correction for layer codes, and we did this with HDPC input, I guess also with LDPC input. And we have some numerics to support this result. And these layer codes actually support longer lifetime. And also, one thing that I didn't emphasize that much was that we actually can encode larger number of logical qubits compared to the previous constructions. So we can go up to like L or like L over log L number of qubits compared to previously it was mostly constant. And so of course the big open question is still whether or not you can have full self-correction in 3D. But maybe some more tangible questions is how do we choose a good family of input codes for these layers codes, because there's quite a bit of freedom. Like it even depends on the specific generators of the input code that you choose. And also, can we take any of these techniques and actually apply it to maybe constructing codes or ones that are even practical with some of these good error correcting properties? Okay, thanks for your attention.
Questions?
So the memory lifetime that you showed in the table, these were lower bounds, right?
Yes.
So what is your actual belief about HDPC with good parameters? Sorry, with good.
Yeah, so I guess from the numerics, it would kind of seem like maybe it is not fully self-correcting, because we kind of see that it's like tapering off a bit near the end.
But should I trust it? This didn't have error bars, right? So.
Well, there are error bars on these, right?
Yes.
There, I guess, yeah. But I will say that one thing is that we kind of, the decoder that we used was the RG decoder for that instead of the this simplified concatenated decoder, which we only realized, I guess, near the end that maybe this is actually more suitable for doing these self-correction experiments. So potentially if we use a better decoder, then you could maybe get better results.
I see. Thank you. What? Actually, for this good rate HDPC, it could be maybe, I don't know.
So if I understood correctly, you were saying that you have an energy barrier, which is like almost linear in system size, like this n divided by log n. And for LDPC inputs, it's actually proportional to n?
N is the input code size, so the number of qubits is actually n cubed.
Okay.
Yeah.
Okay. Then maybe I can ask a different question, so like this lemma that you were using, is it, I didn't fully process it, but does it basically say that if the energy barrier is any polynomial in L, then the lifetime is going to be this W exponential in beta?
If you can have a decoder that can achieve that, then it should be e to the that number.
So if your code is actually self-correcting, then how do the properties depend on the decoder that you choose?
Right. So this is, I guess, the difference between self-correcting and quantum memory that I said a bit at the beginning, which is that, because how would you test if it is self-correcting, right? Like you would have to use some decoder at the end. Even theoretically analyzing it, right? It's just like in some way you have to be able to recover.
Maybe this is a naive experimental question, but if I think of self-correcting as the natural dynamics, like the code word is like the ground state and the natural dynamics return you to that code word, then my test for self-correcting should be that what I put in is still there, and success means I don't need a decoder.
Well,
so clearly there's a difference in definition here, which I'm is I think the
yeah, it's like returning, but it might not be like exactly the code. Like there could be some residual errors that you still have to correct. And I guess it's about like how big those residual errors could be at any point in the process.
Two questions. One, what do you know about the redundancies in your code? Like how many X and Z redundancies you have?
Yeah, so I think the redundancies are exactly the redundancies of the input code. So if the input code has no redundancies, then you'll basically not have any.
Does your input code have no redundancies?
I guess with high probability there would be no redundancies if you pick a random code.
So then my prior to Margarita's question is I think it's not like that. Okay, that's just, okay. And then what is the shape of your barrier, not just the height?
Oh, so what exactly do you mean by the shape?
You can have a square root of n barrier by having a function where e of n goes a square root of n out to distance n, or you can get it by having a linear barrier out to a cutoff square root of n.
I see. So I mean, because there's a lot of patches of surface code, so there could be portions of the surface code that, you know, is just propagating anyons, but like somehow those don't really relate to the logical operator that you're implementing. So for example, on these X layers, that doesn't really have to do with the logical, like you can just have arbitrary anyons floating around, so somehow that is like, you know, I guess in that definition, it's not giving like a good slope for the energy barrier.
No, but is it like you're going up and then you like hang out for a while, like you can have a lot of flips without incurring a barrier, and then you go up again?
Yeah, exactly. You could, right? Because, like, I mean, you could start, you know, halfway through creating this logical operator, you just now create a bunch of errors on the X layers for no reason. So maybe you need to have some definition that like excludes those configurations. Yeah.
Actually, I wanted to ask you a question. Maybe I missed something, but you stated that distance went as n squared, and then you showed a picture of a logical that looked like it had weight of order n. So can you elaborate on that?
That's, I guess, yeah, the one, I guess, is before this. I think this one.
Yeah, I think it was this one. Yes, yes, that's right.
So I guess this is quite a pathological case where like, so this is like from the 422 code, where it happens that the logical operator is exactly half of the stabilizer. And when that happens, then you can like clean it off significantly. But if the logical operator does not overlap with a stabilizer significantly, then you can't really do this process. And then it will still be like around n squared.
You're saying it's pathological in the sense that it was like a bad choice of the input code? Or?
Exactly.
Okay, exactly. I see. So this happens with zero probability asymptotically?
Exactly, yeah.
Okay.
Yeah, high probability this will not happen.
All right. Any more questions? Okay, if not, then let's thank Bailey again. And we'll be back at 4.